and some local beers. Well, hope you liked it. Next time we can go somewhere else, so you know these places now. So the last day, just this morning, and we first tried to analyze the results. We did overnight a little bit, and we decided to do it that way that actually Anke is looking at the runs I started. I was matching up one, so obviously, so I started 2 runs like most of you did as well. And Anke will now show you how we usually look at these runs. So step by step, again, using these visualization tools that you've heard about in the last days. So we will again go through all of them. Just to repeat that, I mean, for me, it's also new because I have my own tool set that I was just, working on for years, but it's not as user-friendly as Tomas' nice tool set that he's written. I may convert to using that as well after this workshop. It's really a nice tool set. Okay, but before we start, I have to ask again the lunch question. So whether anybody wants to eat here in the canteen, because then they have to prepare it at the time. So the choice today is fish, actually. Knurrhahn. I don't know the English word for knurrhahn. So it's just fish, right? Some white fish with potatoes. And the second choice is geschnetzeltes, so classical German dish with potatoes. So to eat here in the canteen, nobody wants to eat here in the canteen anyway, so I think we all go over to the Mensa again. That's settled. Then another idea we got is because, as you have noticed, we are in a new, still quite new institute. We moved in 1.5 years ago, and many of you were interested in the institute. So I will actually offer a tour to the institute and guide you a little bit through the institute. And I think, well, we have to see how long it takes. So either we do it right after the workshop and then go for lunch later. But, the latest time we should go is around 1 o'clock. So that may not work out. So that will mean we at 1 o'clock or go over to the Mensa and then have the guided tour after that. So if you want to stay, so that will probably take until 3 or so. Just a rough guess. So if you can stay that long, and you want to stay that long, you can join for the guided tour. May I ask who would tour? A tour of the institute, a guided tour. So get you to the institute, show you the labs a little bit, and so forth.
That would be after.
Probably after lunch and take until 3 or so. Or we can make sure that if you have to leave earlier, you can also escape during the tour or something. That will be no problem. So we start. I mean, this is a space institute. So our simulations are a very unimportant part of this institute. So the institute-based built space instrument was heavily involved in the Rosetta mission. So we built a lot. Actually, was built not here, but in this institute when it was still in Katlenburg-Linder. So the main part really is this large labs, the clean rooms, which are behind that door that you're not allowed to enter without a guide. So that will be your chance to enter that part of this building. And they burn millions of euro per year, right? And we cost nothing in comparison to that. So we're not important, right? So if you want to see that, this is your chance. So who wants to join the tour? Tina, Achim, Julian, Robin? Okay. Yeah, we'll start probably after lunch, and then it will take until, depending on how fast we are today. The tour usually takes 1 hour and a bit if we see everything, but you can escape. You can just go to the labs, and then, well, you probably don't want to see our offices because they're not very spectacular. We don't have to go to the roof. You may not want to see the kindergarten and stuff like that. So then the tour could be short, and you could leave at 2:30 or something, or 2 if you're very quick. That depends. Right. It's I mean we can aim at finishing at 12 o'clock and then start the tour and then go for lunch after that. Maybe that's a good idea. Yeah, that would be better. So we try that. So we try to be brief. Yeah. Okay, so we do that. Yes. So okay. Try to start at 12 o'clock. Have the tour, which would take roughly 1 hour, And then you know, those of you who want to join for lunch, we can go for lunch then, and then that's it. Okay. Okay. So I guess enough people will come anyway. You can still think about it. So we start now with the first session, and that's again an Ankit show. So what Ankit will do, as I said, we will look at the runs that I did overnight. And again, these runs were not as long as we anticipated. So somehow the nodes we got from the computer center to run our jobs on are slower as we thought, in particular when we share them among people, right? So that is the reason. But still, I think overnight we got a reasonable runtime. So Ankit will show how we usually analyze this now. So Ankit.
I think you did. You talked about several times the same period.
Do you broadcast? No, no, no. You do? No.
Sind die Präsentationen schon online?
Leider noch nicht. Nächste Woche.
Ja,
Should have enough power.
No, I mean, you should take everything. I mean, if you started from very soft knowledge,
So my task was to run two cases at a fairly low magnetic frontal number. So that's magnetic frontal number 4, and this is just about where you find actually dynamo action for this particular Ekman number. If you would go below, you can crank up the rate number as much as you want, and you wouldn't find a dynamo, right? So as I said, you know, yesterday, you need a particular magnetic Reynolds number. So it's a product of velocity amplitude times electrical conductivity to get a good dynamo, to get a dynamo working. So, and the velocity is increased by increasing the radial number. The conductivity is increased by increasing the magnetic frontal number. But there is a limit to it. So you cannot go beyond the critical magnetic frontal number. If you go low, crank up the radial number or the velocity amplitude as much as you want, it would work. So we can make a plot of a diagram, regime diagram, and so if we plot, for example, the radial number, this is one of the parameters we were using, and the magnetic frontal number on the y-axis, and then we mark the regime where we find dynamos, it usually looks something like this. So here you can see the trade-off, that somehow it's the product of the two, which is important. But if you go to large radial numbers, then it doesn't help if the frontal number is too low. And then also, if the radial number is too low, you also never find a dynamo, no matter how large you make the magnetic frontal number. So the runs that I were running, they were basically, so you remember we started with a benchmark, which was radial number 1.1 and magnetic frontal number 5, right? So that is somehow sitting here. And this solution was just drifting. So it was just a nice m equals 4 azimuthal symmetry and was drifting in time. So very simple structure, very simple time. Now, the two runs I had were basically here. So if this is 1.1, I had 1.5, and I had 2, well, it's the same PM. So this was 5, and I had 2, and I had this guy here, and I had 2.0, and then times 10 to 4. 10 to 5, sorry, 10 to 5, yeah. So these are the two runs that Anke will look at. And as I said, if Anke would have given me 3, luckily I didn't do that, then I would have never found a dynamo. So I would have started with this solution. So it has a magnetic field, but all you would see then is you see exponential decay of them. This is good if you want to test whether the code gives you the correct decay time. This is analytically known what it should be, but not if you really want to look at dynamo solutions. Okay, Anke, go ahead.
All right. So first we look at the time series, as many of you yesterday.
You want to look at the lower Rayleigh number first, maybe. Okay. Sorry to interrupt you. By the way. Let's start with the lower Rayleigh number. So basically, what I would suggest is the first thing you do is you look into your log file for that round, and that tells you, you can look at right at the end, and it tells you something, whether there was a regular end to the run or something crashed or so forth, right? That's also important to know. And it also tells you how long, how many time steps you actually succeeded in running and how fast each time step was. So that's this list here. So the first numbers are actually the mean wall time for an individual time step. And there are 2 parts. Well, it's probably not important, but these are the 2 parts in the main time equation I showed you yesterday. So the first, called R loop, is basically calculation of the nonlinear terms, and the second is actually the time update, so the actual time step. And as I told you yesterday, the calculation of the nonlinear terms takes much longer. So this is really the slowest part of the code. And here, for one time step, on average, it took 129 milliseconds. And then the true time integration, so this time stepping, just 28 milliseconds. So that's built-in tools in Magic. And then the whole time step is then 181 milliseconds. And then if you write some output, so we have this n log that tells you how often you want to calculate, for example, kinetic energy, and write it to the disk. If you do that, then the time step increases from 181 milliseconds to 196 milliseconds. So it's not much, but it's if you want to save time, you set this n log step to a larger number. That's what it tells you. And then the mean wall tap for time step is just the average, I guess, between 181 and 196. So it's that. And then below that is it tells you where it started. It stopped the time integration. Somewhere up there it tells you what was the first time where it started, and then it tells you how many steps it has actually gone, and also tells you the step where it stops. I don't know why that is basically the same number plus 1, but okay. Well, and then it tells you you have a regular end of Magic, and then it again tells you the total runtime, the wall clock time, which was 12 hours in the bit. So I specified 12 hours, basically, and it should stop. And that's what it did, and then some wrap up, and so this is the additional 170 milliseconds, and then there's a message at the end that maybe we should change now. That goes back 10 years or so. I try to be pleasant, friendly. And okay, so now we know how long this has run, how much it took. And now, Anke, you can go to the Python and look at the kinetic and magnetic energy stuff.
So yesterday you were looking at the kinetic energy for specific runs. Now, if you have several consecutive runs in a folder, instead of using the tag something, you say all equals true. Then it takes all your runs and displays the whole time series. Hopefully it displays something. Come on.
Why is it so slow? This Wi-Fi is
Should I log out from that node? I don't know whether that helps.
I'm not sure that Go mobile.
Oh, give mobile, that's
Mobile.
so
Otherwise, you can do it.
you could use my notebook, which is direct. I mean, you have a cable here if your notebook is approved by the computer center. Oh, mine is, so you can use mine if you want.
I can use it.
Okay, so what you see now here is, well, I have two runs in there, right, in this directory. The first run was the run where we basically forgot to add noise, right? So this is the line that levels off. So because we forgot to add noise, it still remained basically wave number 4 and just drifting. It was not disturbed enough, right? And then at some point, you know, before we left yesterday evening, I started a second run with the restart file from the first run and added noise to that. And then you see finally it becomes more interesting. So you have noise, which is not a true solution to your system. So obviously you will have a transient. And so there's a lot of wiggle. First the kinetic energies go down, and then they recover a little bit, and then it looks like fairly chaotic, but finally you end up with something which looks more regular and oscillatory. So it's not quite oscillatory. So there's a little bit of chaotic time dependence in there as well. So that's something you typically find when you, so in between, when you crank up your radio number just a little bit, so this is the straight line basically, somewhere here. And then if you crank your radio number up a little bit, you sometimes find oscillatory. So that's like, well, it can be different stuff. So it could be, for example, just a breathing solution. So you still have the wave number 4, but this, just the amplitude of that oscillates while it moves. It could also be something else. It could be wave number 2 and 4, for example, in there, and they drift with respect to each other. And while they drift with respect to each other, sometimes they amplify each other, and sometimes they make, well, they overlap and make the total energy smaller. So that can also happen. And I guess that's maybe what happened here, right? So and that at the end gives you an oscillatory motion, but if you crank up the radio number just a little bit more, it usually becomes chaotic. So this is a very small window where you become oscillatory motions. And, I mean, if you read people's paper from years ago, where they had not a lot of computing power, they typically looked at close to onset or analytical methods or something. For them, oscillatory motion is solutions are very interesting. I mean, you can do something analytically with that. That's an advantage. But keep in mind, for the true dynamo, it's a very small window where you find that. So it's very unlikely that any planet or something is in there. It's not excluded, but it's unlikely. So Ankit, now you want to look at the magnetic energy as well? Ah, it's slow. Too slow. I mean, if you want to do graphics output, that's maybe impossible.
Well, my notebook is also broadcasting at the same time. So.
Yeah, you wanted to switch on my notebook. No problem doing that. So this is the magnetic energies. Again, starting with wave number 4, drifting solution, and then disturbing it to get to something more realistic, and you can see that in the magnetic case, it at the end becomes fairly constant. So there are still oscillations in there, but the amplitude is very, very small. And again, see the transient when you go from the drifting solution to the more complex solutions. And what you also see is that the energies go down. So that probably means, I mean, if you crank up ready number, right? And you would more or less expect that you drive the system harder, and that therefore the flow amplitude increases and also the magnetic field becomes stronger. That's not really happening in this case, and the reason is that somehow the simple solution just double solution, and some of it's optimal for creating magnetic field. But again, a very small window where that happens, right? And then later on, once you have a chaotic solution, then indeed what will happen is that you crank up radius, you crank up velocity, and then you get a stronger magnetic field. You see that in a minute. But so this is a special case. Okay. What do you want to do now? Look at the graphics or spectral. Yeah. I mean, we already saw that the solution becomes more time dependent, more chaotic, and that tells you already it can't be just one wave number drifting around. Right? That's very unlikely that gets to more complex time. It's very likely also more complex spatial structure in the solution. So you want to look at how complex that actually was, is the rate number. So at some point, we should see something, hopefully.
Maybe I can use your notebook.
Yeah, you can. Certainly. We tried that. I don't find any plug where I can plug in the display or you can ask Baron. So you can go to the larger rate number and look at energies maybe if you want to do that. That was, or maybe it's not trying it. You tried something, you're waiting.
Yes.
So or you want to try to use my notebook.
Yes.
You cannot hook into either room of yours. I mean, in theory, I should be able to connect.
No, but do you have a terminal plan? Check so.
That's a good question. I guess I have. What usually? It's too bad we cannot hook up this thing. So as you see, we have a problem with the speed, and the reason is that Ankit tries to do it via wireless LAN, and that's too slow.
And I'm also broadcasting.
And he's broadcasting on YouTube, so that's all that together is just too slow. So we'll find another solution. And while we try to find that solution, you can look at your results already. Do what we just did for your cases.
Well, but I don't know.
If you open your
So it will be fast. Keep copies to your data on this. You want the data on your
Yeah,
if typing takes such a long time.
this will also take a long time. Yeah.
So what is it?
there is, but it's okay.
What can we not?
Don't have any room.
Why not?
That's maybe we should have I have a zero, but I don't have. I get back to that now.
Why not?
I mean, how can I access it? Just
Warum kann ich nicht eins hochgehen, aber unten
weil auch dann
normal dicke Seite 1.
Ja, auch allein. 400.000.
Ach doch, doch, das ist der Radius Reactor.
So, I think what we can.
Deswegen gibt es minimal bis zum Radius Reactor, das ist etwas selten. Aber das ist eine Reaktion. Du das für den Platz genau. Ist der Radius durch den Außenradius.
I understand when it came from.
What's the login to our institute's network? Is it logged into MPS?
SSH should be no, first year using the
Ja. Das ist natürlich
Yeah, very confused. I think if you want to use mine, it's there. Well, that's faster, but I think so it's not minus x, so you won't. Now,
So are we guys to run overnight? 400 times? So we put it up for 15 hours and 1 million steps and finishing 40%. That's good. So just look at yeah, well, you yeah, that's what we can just I mean, if you extrapolate it outside, it's going to be always a time only if you far enough. Very, very small scale.
If you go,
Yeah, it's
can you also
should be
and open this thing.
Posso exportar? Não deve estar eventualmente.
And you can also specify the number of points you want outside. But if we study to software services, you make it very big. And there are gibt's a form. Yeah, it's just yeah. Somebody
Ideally, we would, somehow bring it up,
Definiertes Grill und das in eigentlich musst du ja alle orthogonal, das heißt eigentlich diese Gesten kriegen, ja irgendwie sowas machen. Eine Funktion, die du handelst, ne?
Switch to white background.
Das kannst du halt exakt berechnen. Welche Form geben wir immer? Oft, wenn du die Sekunde nimmst, dann rechnen wir auch die Gewichte auf, das sind ja das
Full size is should be like 4 times that.
Oh ja.
Yeah.
Wirst du
Can you increase the font size? Ja, Buch. Sag mir Buch. Nee, das passt nur. Was wir hier haben. Auswahl. Ja. Ja, also wir haben nicht die passende Stufe einfach. Das. Ja.
Das ist ein bisschen zu schnell, aber
Yeah. So can you increase the font size so that people see what you're typing? I mean, it's not too essential, but or just
sowas
change the screen. Can you save these settings?
Yeah.
Please do that.
Bei denen ist der eigentlich was das sind ausgedacht.
What do you want to watch there?
That's better. Here it's big.
No,
Background.
change the default background. Do
Oh, you can even, that's nice, you can choose the color background. Can you choose a pink background, please?
Können wir auch so zu checken.
Aber
Okay.
so dann ist wieder raus. Wieder weg.
So now look at it's also getting close, or you want to keep working there?
So ein bisschen einsteigen.
I prefer. I think it's better to move here, right?
Verwunderlich, dass wenn Dynamos so aussieht, aus dem sehr irgendwie stark visualisieren. Das ist ja ähnlich. Das ist schon ein
Ja, das sieht auf jeden Fall aus, als ob es noch nicht so eingefallen ist.
erstaunlicherweise die nächsten mit der
Aha, du hast auch gleich mal gespannt.
Genau. Also das heißt,
Und dann immer so eine kleine Ecke. Ja, das ist halt das.
where you can sit down and it's more expensive.
This is which way? The larger way.
Yeah,
Ja, oder halt, man macht es dann immer falsch, weil man die App zum Beispiel auch die alten.
Okay, so we can show you something. The problem was that Ankit's notebook where we wanted to show it, it's not approved by the computing center. Enter the line here. So we changed now. And so this is now from the end of my run at the lower ready number, the magnetic field close to the, somewhat into the shell. And you can see that wave number 4 symmetry is still fairly dominant. But there's also something else coming in. So it's not the pure wave number 4 anymore. So it gets more complex. So Ankit, now maybe you can show the spectrum. So in the spectrum, if you look at the spherical harmonic degree spectrum, or wave number M spectrum, we should see not just the peak at 4, but we should see a little bit more. Yeah, that's the kinetic energy. So we see still the 4 peak being dominant, but then you can see there's also other stuff which is weaker, but certainly changes the solution and makes it more complex and also more time dependent. Right? So now, yeah, we can look at the magnetic spectrum as well. Yeah. If you just say magnetic spectrum, it produces both. So the magnetic spectrum is seen here. So, well, so we have colloidal and toroidal in the shell, so the averaged contribution from the different spherical harmonic orders. And then we have it at the coronal boundary. So this is the field that you would see as an outside observer. So therefore, it's interesting to compare this one to any planetary knowledge you have. And you can see that the wave number 0 has a peak. So that's the axisymmetric magnetic field. And this peak comes because of the dipole, right? So it's a dipole-dominated magnetic field still. And therefore, it's mainly axisymmetric. And you have the peak. And then you also see the second peak, so that it decreases a little bit, a second peak again at 4, simply because the flow structure has this 4-fold symmetry, and that's also the preferred length scale then where you produce the magnetic field. So that's what we see here, and then you can see the spectrum is then also dense, and it decays like many orders of magnitude. So that means by resolution, here is still good enough. And we started with the resolution we used for the benchmark, and
I'm not so sure.
You're not so sure. Well, I'm satisfied. It's several orders of magnitude. That's good. Okay, now maybe you can show how to time average the output. So,
Time average, you just say average field.
yes. So now we want to look at time average quantities. And of course, it doesn't make sense to start at 0 because we had all these transients. So you don't want to have them in. So you should look at your kinetic energy versus time and decide basically where do you think you have equilibrated to more or less the solution you expect. So in a statistical sense, so you have the impression that more or less the energy on time average stays constant, and then you have oscillations around that. If you think that's okay, and that's where you should start your time averaging. So you can look at the spectrum, and here you see at the end you get this oscillation with a little bit chaotic behavior, and that starts roughly at 21 or so, right? So you can then say this averaging routine. XP line, what's that? Why don't you stay with the average routine? There is the averaging. Tell. Okay. I could edit the line to show you. Okay. 21. Maybe you want to go to 22 or so to make sure, but it wouldn't matter much. Okay. Now you can average. Use the averaging routine. So what this averaging routine does is it looks at all the or most of the time-dependent quantities you've stored somewhere in your output files, grabs them and averages them, starting at time 21, going to the end of your run. So you run this Python script, and then it produces a lot of output that you can access by just saying a.ek, for example. right? So if you say A dot EK, it's the time average kinetic energy, Ekman number, sorry. It's the Ekman number, that's constant over time, right? We didn't change that. So Ekin, yeah. Okay, but quantities we are typically interested in is, for example, the magnetic Reynolds number. So A dot Rm, does it exist? Ah, Reynolds, okay. Could be is it the magnetic or the Reynolds? And that's U Reynolds, okay. So probably A dot Reynolds is the magnetic Reynolds, right? Because there is U Reynolds exists. So if you type
U Reynolds should be the same actually. I think both are. It's magnetic.
It's magnetic.
Yeah, it's right. PM and PM is there.
Okay. Okay.
It's just because.
Okay, so that's the Reynolds number. Yeah, well, could be. That's about.
Let me check.
It's exactly the same.
Show him the SS.
Okay, Thomas has to check whether the Reynolds number is the magnetic Reynolds number or just the flow Reynolds number. The magnetic Reynolds number is just the flow Reynolds number times the magnetic frontal number. So that would be easy to convert. I would expect that for this one, the Reynolds number is still, the magnetic Reynolds number is still in the 50 range. So I guess it's the magnetic Reynolds number, but
It should be
that.
There is the RM. RM.
There's RM. Okay, let's look. So maybe I was wrong. So no, it doesn't exist.
Okay, wait a second.
You can see that these scripts are also fairly recent. So Tamar wrote a lot of this for this workshop. So we also have to get acquainted to that. So you can look actually at the end of the log file, right?
So it's the RM. Reynolds is RM.
Reynolds is RM. So 50 is about what I expect for that. So it's the magnetic Reynolds number. So that's something you're typically interested in to characterize your dynamo, because it's the ratio of magnetic field production to ohmic diffusion or something. So that's a good measure. And for Earth, for example, RM is supposed to be around 2000. And as Oli told you in his presentation, you can reach that 2000 value if you crank up your Rayleigh number large enough, obviously. Right? There's a problem, however, and that has to do with the Ekman number. So if you would, for this Ekman number, crank up your Rayleigh number, at some point you would lose the dipole-dominated field. So if you would plot this diagram further, there is a transition which looks like this. Well, so you have in this regime a dipole-dominated magnetic field, and then at some point later, maybe we'll still have, some of you should find cases where the Rayleigh number is so high that you find a multipolar magnetic field. So the dipole is not dominant anymore. You would see this when looking at the spectrum, for example. So I told you, for example, the M equals 0 peak, that would come down, or you should look at the degree spectrum. And we also have a measure which is called dipolarity, and I can show now the time average dipolarity. So what that is, basically, you look at the field at the coromantral boundary, and you look at the RMS field contribution by the dipole, or the axial dipole. Is it the axial dipole? By the dipole. And then you divide this by the total RMS field at the coromantral boundary. So the question is this the square root of the energies, or is it the energy ratio? Yeah, it's probably energy ratio. And so that, I did simply. Okay, that's what, yeah, that's fairly large. So it's probably the square root. So that's the RMS ratio of the magnetic energies, of the square root of that. So RMS field strength. And at this value, 0.64, it's fairly large, so you would call this dipole dominated. And you could check it by just looking at the field at the other boundary. And you would see it's mainly one color in the north, other color in the south, blue in the north, for example, red in the south, and that's a dipole dominating magnetic field. For Earth, that value is much higher. It's around 0.9 or something. So, but still, it's dipole dominating. So if you would have a multipolar case, that value drops significantly. So it goes down to 0.1 or even below that. So if you have a large Rayleigh number. Now, as I said, if you try to reach RM, so an Earth-like magnetic Reynolds number for this setup, you have to crank up a Rayleigh number, and you can reach that at some point, but the field would not be Earth-like anymore. It would be multipolar. So what you have to do is, you have to go to lower Ekman numbers. And if you move to lower Ekman numbers, then this boundary moves to higher Rayleigh numbers. So you can reach an Earth-like magnetic Reynolds number at Ekman numbers of about 10 to minus 5. And it's still then dipole dominant magnetic field, so it looks very Earth-like. These cases are already fairly expensive, so you don't want to run them on a daily basis, and certainly we cannot do it here. But just to make you aware of that. Okay, Anke. So there are more properties we typically look at. For example, the Alsacer number. And remember, the Alsacer number is a measure for the field strength. So, or it's a ratio of the RMS magnetic, well, E squared, so the RMS magnetic energy over the Coriolis force. And there are two values. So we have the RMS Alsacer number in the shell, averaged, and then we have the one at the metal boundary, 0.64, and it's the same. Yeah. Okay, and that is typically a value you can use to quantify magnetic field strength, and that's now a non-dimensional measure, so it's a ratio. And for Earth, you can calculate this as well. So you know the rotation rate for Earth, right? And you can measure the magnetic field. You know the density roughly. That's all it enters, and the conductivity. You calculate for Earth, that's around 1. So the ratio of Lorentz, you can think of this as the ratio of the Lorentz forces to the Coriolis forces in your system. For Earth, that's around 1, and here it's around 0.6, which is not too bad. So, and we tend to think this may be one reason why these dynamos look fairly Earth. Well, in a sense, they are Earth-like. It's not. If you look at the details, they're not. But the Alsacer number, for example, is not too bad. And the magnetic Reynolds number here, it's too low, but it's not orders of magnitude. So, and you can reach this if you go to lower Ekman numbers. Right? Good. So what else should we look at, Ankit? ROL maybe.
Yeah.
So another measure we look at is what we call the local Rossby number. So that's a bit special. So the Rossby number, you may know, is defined as, so Rossby number is U over D omega, where U is an RMS typical field velocity, T is a typical length scale, and omega is the rotation. You can think of this as the ratio of inertial forces in the system over Coriolis forces. So that's how it's typically understood, and people typically take the length scale B to be the shell thickness, right? Uli came up with a new idea to quantify that maybe a little bit better, and this he called the local Rossby number. And what he did is he not used the shell thickness, but he used something like a typical length scale of convection. The reason behind that being, if you look at the non-linear part of inertia, which is the attraction. So this is U times grad U. Okay? So you have a gradient in here. So the length scale basically should reflect the influence of this gradient. And it doesn't necessarily make sense to use the shell thickness here, right? Because the flow has another much smaller length scale. So that's why he used well, a typical flow length scale here that you can calculate based on the solution, and that's done by magic for you. And then you come up with a local Rossby number. For this case, for example, is 0.02. Right? So what does that tell you? Why is it important? It's interesting if you think about this transition again, because this transition from dipolar to multipolar cases typically happens at the local Rossby number around 0.1. And now Udi's simulations show that this is a good measure independent, more or less, of the other parameters. So that's a good measure independent of the Ekman number, for example, right? As I've told you, when you decrease the Ekman number, this moves further out, right? So to different Rayleigh numbers. So that's why if you decrease your Ekman number, you should always increase your Rayleigh number to stay in the same regime for dynamo action. But it's always at the same local Rossby number. So, and the Rayleigh number is an input parameter. This is a result. So the flow amplitude goes in here, and the length scale goes in here. You don't know this in advance. That's nothing to impose. It's a result. So it's a result to say that this boundary always happens at the local Rossby number of 0.1. That's just numerically found. There's no analytical reasoning for that. It basically tells you that to get a more complex magnetic field and also field reversals that only start to happen around here, you need a stronger inertial force or a stronger advection. And advection typically is, well, that's where you mix your fluid. So different length scales interact and you get turbulent mixing. So you can think of this that you need more interchange of length scales or interaction of different length scales to get reversals or more complex magnetic fields. So, but that's just an interpretation, right? So now I can ask, what is that for Earth, the local Rossby number? Because for Earth, we know we have reversals, right? And that's a difficult question. I mean, Oli told you if you would, for example, take this literally that you need 0.1, and for Earth, you would end up with length scales. Typically, you would say basically that the typical length scales are 100 meters or 10 meters or so, very small. And people don't think that's reasonable. So it's not quite the answer. So there is still some open questions here. So that we don't know. So it could be, for example, that Earth reversals for other reasons. The reversals come from for other reasons, not because you are at a transition from dipole to multi-dominated regime. That we don't know. Okay. So, okay, what else can we show? Well, so I mean, you can play with this around. So once you've averaged in time, you can use these values to fill your tables to make regime diagrams or whatever.
Well, print A, just change the direction.
Yeah.
Okay, yeah, give print A.
Everything that's
That's
look at everything. It's better.
it's not really human readable, or it's human readable, you don't know what it means, but if
Yeah, you have
if
to
you
know
want to
what-
make a table,
Yeah, that's the way.
right? If you want to make a table and then plot that table to make regime diagrams, you can use print A and then access, if you want, for example, want to plot the time average quantity versus Ekman number. This is your Ekman number. The second number in that table would be the Ekman number.
First
and
one is
then-
Rayleigh.
Really,
First is Rayleigh, and then you have frontal, and then you have magnetic frontal, and so forth. So that you can use to create tables, and these tables you can then use to plot, curves or regime diagrams or whatever.
Yes.
Once you've run, so you would run at different parameters and just copy that string in your table, and then you can look at parameter dependence, make some curves or whatever you want to do. So all this, of course, is written in your online manual, so you can check what these different numbers actually mean.
Yes.
Wow. So now we can 10, 12, 10. We can briefly look at the second case. So yeah, 10:30. 10:30. Yeah. So let's briefly look at the second case. So now we will briefly look at the second case. So for this case here, magnetic potential number 4 at radian number 1.5 times 10 to 5. You still had wave number 4, and it looked quasi-oscillatory, your solution. Now we crank up the radian number by a third, basically, to 2.2 times 10 to 5, and see what happens then. And I can start again with looking at the kinetic energy, and there again you see a transient, and then suddenly the stuff becomes chaotic. So here, obviously, more interesting things happen, but you may wonder, there's also something happening. You see, you have a burst around here, right? So there may still something happening. So it may be that your solution is not quite settled, and you would want to integrate maybe a bit longer before you start time averaging. So this may not be statistically settled. I mean, you can start time averaging here, but then this burst would be a significant part of your run. So it may not be a good idea. It could also be that this is a physical phenomenon, so it's a true part of your solution, but that which you don't know. Mind you, this is roughly from here, let's say here to here. Well, or yeah, so this is 15. So that is, well, nearly 4 magnetic diffusion times. So it's quite a bit, right? So it may already be okay. So you would expect normally that the system has equilibrated in that long time scale. So maybe it can be bold and start averaging that guy. And then, use the A point something, and then make your table and use this as a new plot in your regime diagram. So you can also show now maybe the spectrum, Ankit. So more complex time behavior tells you the spatial spectrum should be denser, so it's more complex. Maybe you can look at the degree spectrum for once. So, okay. So the blue is what? The blue is to right. The blue is to right. So here is now the spectrum, and where's the spherical harmonic degree? And you again see that the dipole still clearly dominates, and it decays at least an order of magnitude. Then you have like a flat spectrum, and then it decays like 3-4 orders of magnitude. That's a fairly nice spectrum. So you would say your resolution is good enough, and it's actually also a very Earth-like spectrum. So you have a dominant dipole, and then you have a flat part. And so flat part means roughly wide spectrum here. And then for Earth, actually, we can go only to degree 14 or something. We don't know the smaller part, which would be here. So up to there, Earth is roughly wide. And we don't know when it decays for Earth. Likely much later, right? Because Earth, you have higher magnetic Reynolds number, higher Reynolds numbers, likely later. But this part is quite Earth-like. And now we can look at the solution. You plot the radiomagnetic field at the outer boundary or something. You can also, show versus M again. So the wave number, again, because the axial dipole dominates, you have wave number 0, so the axisymmetric part dominant. And then, well, before you have seen that the 4 is still peaks out because the flow has that symmetry. Here, not so much, right? So here it's fairly dense, so it's hard to predict what's going to happen. So let's look at the solution. Well, first of all, you see it's still fairly large scale. And wave number 4 is, well, okay, there's still something in there, I would say. You can still see a reminder of that. But also, obviously, it became much more complex. And you can see it's dominated by a dipole because it's mainly blue in the north and mainly red in the south. So that's what we saw in the spectrum. But it's still fairly simple, right? So well, that's probably, so in the large scale, you may call it Earth-like. In the small scale, it's likely not. But for Earth, actually, we cannot access the small scale magnetic field. You remember why? I mean, Uli briefly mentioned that. Why can't you access the small scale magnetic field that is produced by the dynamo on Earth? Because, well, we have the crustal magnetization. Achim is an expert on crustal magnetization. So as the crustal magnetic field is also magnetized. And you cannot separate, well, if you make magnetic measurements, you can only separate the magnetic field which are produced above you, where you measure, above the place where you measure, and below the place where you measure. And if you measure Earth's surface or with a satellite orbiting Earth, the crustal magnetic field and the core field is underneath you. So following Gauss's laws, you cannot really separate them. Right? That's not possible. There are two other ways to separate them. One way is you know that the crustal field is small scale. So it's mostly m equals 14, L equals 14 or smaller. So that's typically what you do. You say everything larger is internal field, and you can see that typically also at the spectrum. So when you look at Earth magnetic field spectrum, the dipole sticks out at the surface, then it decays, and then it becomes flat. And that happens roughly at degree 14. So you know that part is likely contaminated by the crustal magnetic field. So that's why you cannot access this. Another way to access that would be the time dependent, because Earth's crust is fairly immobile, right? So the crustal field is not changing on fast timescales. Fast timescales meaning 100 years, 1,000 years, 10,000 years, right? So if you have measurements long enough, you could separate the two, right? So because the internal field is changing on timescales of 10 years, 100 years, or a bit longer. And that's where the problem lies. So you need longer timescales, and we need more magnetic satellites to orbit Earth for longer timescales to achieve that. We already do that now, but it's not easy. Okay. Okay, what else can we show?
Well, we can look at slices or something.
You can look at slices. Yeah, maybe you could show one slice at least. So this is a median slice, that's how we call it. So it's a slice which goes through from north to south. And I guess what I could show you is an axisymmetric part. Is it, or is it not?
No.
Okay.
It's where does it give me error?
I don't know. Sort of range. See, it plots something. You know that. You think that's wrong, or you don't know where you actually plot it. Or what?
Well, it's supposed to be 0 degrees longitude.
Yeah, but you know certain whether that is true. Okay, so we have to look at this range. He gets an error myself.
Oh yeah, I was just trying to top that.
Oh, it's not. It's not.
It's just, yeah, it's not.
So this is the azimuthal magnetic field, which goes around like this. And if you plot the axisymmetric part, that's a measure for the toroidal magnetic field that we cannot observe outside. So you would typically look at something like this to get a hand or an understanding of the toroidal magnetic field. And you can see that it has very strong patches here. And if you remember what Oli told you, this is actually where these convective columns wind around the magnetic field, so stretch it around in azimuthal direction. That's why you get these two strong patches here. And that's the main production of toroidal magnetic field in this kind of simple dynamos. Okay, I think we run a little bit out of time, as you may have noticed. So Jörn is already waiting to give his talk, but he may give us a few more minutes because you may want to grab some coffee and some drinks and cookies. And this would also bring us to the end of the hands-on session. And I don't know whether you had the chance actually to look at your runs. So a little bit. So the original plan was that we collect data from you, each of you. So Ankit would collect them. For example, the magnetic Reynolds, so these time average quantities. So the task would be that you look at your kinetic energy, you decide whether it's equilibrated or not, average in time, the part that you think is statistically equilibrated, and then provide Ankit with this string, the print A. And then Ankit could use this to make a regime diagram. Right? And I don't know when he will be able to finish that regime diagram. So we should end up having something like this, right? We'll see. We'll see. I don't know. Probably we won't be able to finish this today, but we would finish this next week and just distribute it among you. That's okay with you, I hope so. So if you want to do the analysis now or later, please do it. If not, we can also do it. We have access to the data. And then tell you what we should have seen. And I wonder whether you could also take the data home. That would be another option. So you could, did you thought about this? Did we find a solution? Not really, right? So what we could do is we could put the data on Dropbox or something.
Well, I can upload it to the workshop website.
Or we upload it to the workshop website. And if you remember your user ID, we will sort it according to the user ID. You would then be able to later access the data and analyze them at home. Right? As long as you have Python at home, I hope you all have that. If not, you should ask your computing center. Then you can also do the analysis at home. And of course, send us emails or phone us or whatever if you don't manage and you run into trouble. Right? Okay? Okay, then I suggest we have a coffee break now, and maybe in 15 minutes we start with your talk. Ah, you have to.
Gebe ich Ihnen ja prinzipiell recht.
Mich hat das gezwungen.
Ach ja. Und wann war dein Vortrag? Heute Morgen oder gestern Abend?
Nee, ich hatte gestern Abend ein Skype-Meeting. Was war ja gestern noch von der Ja, genau. Ja, auch von der Sonne.
Ja, genau. So wie wir sie auswählen.
Ja, oder auch nochmal das Platz machen. Ja, heute Morgen habe ich das kleine
total diese Bereichswerte von eher kürzer halten. Okay. Yeah,
because you specify that the boundary
genau, machen wir auf jeden Fall auch. Das meiste
I would expect that it's going to be good. I mean, so we divided B
mal an die letzten Wochen.
and B internal is the whole thing. The external part that's going through and the internal that is being produced. Okay, so what's here is just the B external. Something where you put your skin. But yes, you would say there might be a set of that. Yeah. So yeah, so this is like you put it in, and then it's the external field. Whatever goes in becomes part of the internal field. But the internal field is one your computer is what you call also fixed field you can give it inside. So internal field is whatever you compute plus whatever the external field that goes. So there's not easily the possibility to on the inside as a 3D file. I mean, the internal field ideally also contains component of that. Let's say I want to having only a base and see what you can
Mach mal ein Spaghetti.
You mean you want a radial field inside? I want a radial field inside. Then look at this init V1.
Weißt du noch, ob du noch so ein
That's actually okay, but then that's somehow think about having okay, where's my sphere? Put it somewhere to feel. Also the second one. But then that's not. But then when you're looking at the external field, it also has components from the external field. Send it to me, or you can just create a file and do it. Should we have a standardized name? Yeah, I mean, it's something like something that is okay, so if I would like that should more defined, then still few or I say but that's something new. Yes, but looks really the external field that is implemented is always axisymmetric, and you select an F. And it's
morning.
And what do you do then? Was it really the boundary? Well, first you implement it as a boundary condition, and then you start computing like what happens inside, how does it now. And then let's say you find that yes, that would also mean that it goes axial through the yes, but whatever goes inside becomes part of the internal. But that's it. Yes, that's computed. If I define an external field of the boundaries, whatever goes inside, the continuation on the inside is taken into account. Yes, on the inside. So if I want to define 1/r radio filters. Or something like that. I mean, you need to define it. You go to field, which you can. Yeah, but I mean, the point is, do I need to start more or less from the beginning to define a new field variable, or is there already a kind of infrastructure of that?
Yeah,
Then maybe it's more, a little bit more. I cannot easily define alpha and typical content.
yeah, exactly. But it's not that general. Well, you can define an error. That's in it for now. But you can describe it in terms of.
But it's really the definition is be external and then what is written in update being. So let's create this. Call it string A, but now I should call it. Oh, does it come directly on Atlas or on the on? Oh, it's a second problem.
I'll make 16 SCPs.
Because we were new.
No, yeah, so I mean, I know that's how university. So in the UK, you go to a conference. Hosting conference. You go to the forums,
Whatever, and he wanted to get rid of the castle because it was too expensive to run, I guess, right? So he gave. That was really great. kind of different depths. So at the beginning, you don't know which depth you should actually look. That's possible. So maybe you should start talking to him. If he's still around, is he still so this second version there are some output features. The problem is they're not part of this code. My code just tests it. They're not in here. So we need but Dingo has a code foundation that takes the vector field and puts it over, which is sort of a different depth.
Ready? Hallo? Hallo? Ja, gut. Mhm. Ja.
Pas devant la webcam.
Nein.
Au fond, même. Vous allez avoir une place là.
Nein.
Oui, oui, no, it's sorry. I'll make it this morning.
What?
No, I couldn't make it this morning. So he said sorry. No, he had to go back to Paris.
Okay.
Ja, aber
So
einmal die Woche?
well, he said he wants to do it.
Okay.
You already have your own presenter.
I have my own.
Nein.
So now something different. Well, somewhat different, not totally different. So I thought it may be interesting for you to hear something about not magic, but a different code, which is called pencil. So Jörn Wallicke is an expert in the pencil code, which has been developed initiated by Axel Brandenburg and others, and it is around for 20 years or so, I would guess. Maybe
Yeah, it was initially developed on a summer school.
in the summer school.
Yeah.
Same amount of people for 2 weeks and more or less writing. Code
So
initially.
it's used heavily in the solar community to simulate aspects of stellar dynamos or solar dynamo, and Jörn will tell us a little bit about that, but also to simulate other fluid dynamical problems or even particle tracking or something like that. So I think it can do a bit more than magic in the moment. It can also manipulate you can solve in a box or in a spherical shell, maybe other geometries. Of course, magic is just a spherical shell. You cannot help it. So let's hear what Jörn has to tell us. And he is actually in our institute for 2 years, I think, more or less now.
Yeah.
So he to make a PhD with Axel, I think, right? And then was there in between postdoc, or did he came to our institute right away?
Kind of, yeah.
Kind of right away. So since 2 years he is here. We are very happy to have him. And he's actually, as you may have guessed, working in the solar department while we are planetary department. So go ahead, Jörn.
Yes. Hello, everybody. So I will give you some ideas about stellar dynamos. Of course, the topic is so broad you can teach probably a whole semester about it. So I will just glance to different problems what we have, show some little results, and give you a bit some information how the stellar dynamo or the solar dynamo might be different from planetary ones. So I'm, as Johannes said, Jon Wanneke, working at the Max Planck Institute, currently a Marie Curie Fellow, and and I use the pencil code, so we also do nice T-shirts. But I will come to the code also a bit later. So I will focus for the stellar dynamos mostly on the sun, because the sun is something we can observe quite well, and we know about the sun the most, I would say, compared to other stars. So, and when you look at the sun, probably similar picture if you look at the sun, if you have the right glasses, so don't look at the sun without glasses, protection glasses. So what you see, this is a continuum image of the sun, and you see this dark features on the sun, which is called sunspots. And when you make a zoom in, it looks roughly like this. So you have here a granulation pattern, and you have here a dark region in the penumbra. And if you have very luck with observation, you can even produce movies like this. So this is a real sunspot observation done from our colleagues in Sweden at the Swedish Solar Telescope. And what you see here very well, you have a granulation pattern, so convection around here.
It's the evil eye, right?
Yes, it's like so. You have this dark, very dark patch in the middle, and you have this is probably aligned convection cells which form this. So the interesting thing is for us is this is a magnetic feature. So what you see the difference is the difference in temperature. So this is around 6,000 Kelvin, and the middle is around 4,000 Kelvin. So and the difference is that you have here around several kilogauss field, and because you have a strong bundle of magnetic field, this prevents the convection to do their job, so to transport heat to the surface, and therefore the heat transport is a weakness here, so you see then that's why it's darker. And this is very interesting. And if you now see the same picture from here and look at a magnetogram, so show the different polarities of the magnetic field. So white is one polarity, black the other. And you see that you have there where you have the sunspot very strong features of magnetic polarity, but also there where you don't really see much in the continuum image, you have a lot of magnetic field. So you have different features of magnetic field in the sun, and this is also to see, of course, in the background of the structure of the sun. I will come to this a bit later. So you have the core, the radiative zone, which goes from 0.3 to 0.7 around about the solar radius, and then you have the convection zone. And in the convection zone, because you have convection, so you have turbulence, so you can amplify a magnetic field and produce features at the surface which look like this. The interesting thing is that if you look at these features, if you follow these features, so these sunspots, over many years, and already Galileo Galilei had started to count them and find that there is a very nice cycle. So what I'm plotting here is the time, so from 1880 to 2010, and then here's the latitude. And the color coding is how much area is covered by these sunspots. And what you see very nicely, you have this cyclic behavior, which is around for each cycle 11 years. And the sunspots start to appear actually at high latitudes, at the beginning of the cycle, and then appear closer to the equator when the cycle comes to the end. And this is quite regular. Of course, you have, in the time of the sun, you also have minima where maybe for several years there was no real sunspot measured, called the Maunder minimum. And the important thing is that this is related to a magnetic cycle. So this is plotted now at the surface of the sun, the averaged radiomagnetic field, so which is perpendicular to the surface. And you see here over time, you see the different polarities changing with the cycle. So you see still this, what we call the equatorial migration of the activity belt. So you see, beginning of the cycle, magnetic field is strong at high latitude and then move gradually to the equator. So you have a different polarity in each hemisphere and a different polarity for each cycle. So, and if you want to do modeling, of course, you want to reproduce this. But it turned out to be not that easy, actually. Coming to the numbers. So I steal the ones from the Earth core yesterday from Thomas. But just to get you a feeling a bit, so you have the Ekman number. It's a bit similar to the Earth core in the sun. The Taylor number we use often in the solar community, which is basically just related to the Ekman number. So it's just the inverse of the squared. It's very high. The Rayleigh number, we define it a bit differently because we are in a bit different regime. So we actually can't use the Bose-Nest approximation. I will come to this a bit later. So we define it a bit differently, but still it's about convection against diffusion, and you have here different Prandtl numbers. So the fluid Prandtl number is very low, and magnetic Prandtl number is higher actually in the Earth core. And of course you have the Rossby number, and I actually prefer not the Rossby number, the Coriolis number, which is basically the inverse of it. This is just because when you use the Coriolis number, it tells you if it's large, you have large rotation. So it's, for me, a bit more intuitive, but it's more like a matter of text. So you are, what we said yesterday, in a regime where the Coriolis number or Rossby number is around 1. So you are actually in between the rotation-dominated and convection-dominated regime, which just makes it very interesting, but also very complicated. The Reynolds number is very high, of course, and I think one of the main difference to change it as a change to the Earth core is that the magnetic Reynolds number is very high, so 10 to the 9. And the other number is the Peckley number, is basically like the Reynolds number, but just for the thermal diffusion here by chi, it's also quite high. So these are the numbers, but this is of course not the full picture. So if you go look at the plot again here, you see that here's the radius going from, so the convection zone from 0.7 to 1. The temperature is changing from around 2 million Kelvin to around 6,000 Kelvin. And more important is the density is also changing a lot. And what I did yesterday is actually I download the currently best solar model what we have. So from structure modeling from Christensen and Dalsgaard, and I plotted basically from the model the different quantities. So here over radius, here's the surface, here's the bottom of the convection zone. This is a logarithmic scale. So so the temperature, okay, it's changing a few 2 orders of magnitude nearly. It's okay, but the density is really changing a lot. So you see, especially near the surface, it's changing a lot. The pressure is changing even more, and also the sound speed is changing.
Just a question here. How close it goes to perfect gas? So if you would multiply density by temperature, is it really like giving something close to pressure, or?
Yeah, I think it's. I mean, you have a different gamma. So I think so in the middle, so up to maybe 9.9 or 9.5, you are quite similar to polytropic. So, but near the surface, things get a bit more difficult because you have the difference also from the Earth is you have plasma is cooled by radiation at the surface. You have ionization effects taking place near the surface. And this really makes these temperature or the density gradient is very steep. And this is quite complicated to model. To have overview again, so the density contrast, it's around 10 to the 7. The temperature contrast is around 600, okay. Pressure contrast is even higher. The sound speed is varying from around 200 to 5 kilometers per second. It also means that actually somewhere at the surface, you're reaching velocities which are similar to the sound speed. So you become in a regime where the Mach number is actually around 1. And this is also important for the modeling. So because then you can't use the unelastic approach anymore. So you have to use compressibility. The important thing is basically the pressure scale height. So if you calculate how much the pressure is decreasing in factor of E over a certain height, then this is changing. So the pressure scale height is in the bottom around 100 megameters, so the full convection zone is 200 megameters deep. 1 megameter is 1 million meters, so we always like to use megameters in solar physics. So it's basically you have kind of a convection, so the pressure scale height gives you roughly the size of your convection cells. So from this theory, at least, you should have convection cells which are nearly as large as the convection zone at the bottom of the convection. But if you go further up, you have the pressure scale height is around 0.1 of the megameter. So it's like just a few 100 kilometers. So your convection cells are very small. So this means your typical scale where your sifting system is forced by the convection change with steps. And this has lots of consequences. It makes it actually
One question, do you actually know the scale at the surface? I mean, do you have the resolution to look at smaller scales than this?
No, but I mean, you see that the granules are around half a megameter.
Yeah.
Roughly. So you know roughly the scale. And this is where the motion takes place. So the granules have the, when you look at the velocity spectrum at the surface, it peaks at the granules. This is a model. I have to say that actually currently also this model is questioned because we have some method to actually look into to measure velocity steeper down, and some of the results doesn't really agree with these models. So at the moment, this is even open question if this is true. But okay, this is just a side comment. Now I show you some consequences of this. So this is one of the, I would say, currently one of the best simulation resolution-wise what we have. So this is by one of our colleagues, Hayuki Hotta. So this is a non-rotating case, but this is basically how the convection would look like at the surface, but close to the surface. So you have lots of little convection cells. And so this is, So this is also a simulation now with convection and rotation. And so there are two things happening. So it's involved in time, but also he zoomed out from the core, or not the core, the bottom of the convection zone to further up. And it will play again. So you have in the bottom quite large scales. And you see also there you have these, what we call sometimes banana cells. You have elongated, strong convection cells. And if you move further up to the surface, you go in a regime where you don't see so much the rotational influence. So this means now I change these numbers a bit and create numbers for the bottom of the convection zone and for the top. And you will see that you basically have two very different regimes. So you have the turnover time at the bottom is around a month, so the convection turnover time. At the surface is around more minutes. You have velocities which are around kilometers per second, and near the surface is 0.1 or can be even higher. As I said, the pressure scale height is around 100 megameters, around the surface 0.1. So this has, of course, consequences for these numbers. So the Ekman number decreases as or increases. So the rotational influence near the top boundary is much less, as you also see in the simulation. The radial number is roughly the same. The Prandtl number is very different. So there's a difference of 7 orders of magnitude in the Prandtl number. Also, the magnetic Prandtl number is quite different. So it means that the Rossmer and Corollis numbers, of course, yeah, it's around 1. And then at the surface, what tells you Corollis number is very weak, so you don't have strong influence of rotation, so near the surface. And also the Reynolds numbers are quite different. So you have very high Reynolds number at the bottom, still high at the surface, and also the magnetic Reynolds number change a lot. So you have basically different regimes near the surface and near the bottom. And currently, it's not really clear on what scale basically your dynamo is forced. So on what scale the dynamo is operating, or what scale of convection is the dominant scale where the dynamo is generated. So this would mean you don't know really in which regime you are. Anyway, all the regimes are, of course, at the moment not really reachable with simulations. So often we try to just do mostly the bottom and neglect the surface or something, or you do some other tricks. So this is one of my simulations. So this is also shown again somewhere, with not so strong density stratification. You see, this is the radial velocity. So you see this unlogated convection cell. This is the deeper down. You also see this, and so it's basically like this. Cut this over, so you have deeper down these banana cells, and then on the top you have basically convection, which is not really influenced by rotation. Then the other thing is what is different to planets is that you have very strong differential rotation. So this is now contours of differential rotation from one of my simulations. And you see you also have different regimes. So you see here that some of the contours are nearly cylindrical, like here, which means that in this regime, the Taylor-Proudman theorem still works. But if you actually look at the real sun, so this is now taking from helioseismology a method where you can actually look at the sound waves in the sun and can calculate basically the differential rotation from this. This tells us that the differential rotation looks like this, and that the contours of rotation are not cylindrical, so they have a little inclination, or they are nearly radial. So it means that the Taylor-Proudman theorem, or the balance, the Taylor-Proudman balance, is broken. So you have other effects which play a role. What makes it also a bit more tricky is that you have strong shear layer. So you see near the surface, you have a shear layer because the density stratification goes very high near the surface. The influence of rotation is very weak. So basically, the rotation is weaker near the surface than deeper down, and that's why you create strong shear. And the shear can be one generator of a magnetic field. The other one is you have at the bottom of the convection zone. So here's around the bottom of the convection zone. You have other shear layer called the tachocline here and here, which can be also responsible for generating magnetic field. And you can have when you go in the latitudinal direction, of course you have latitudinal shear, which might also play a role. So another thing is when you do simulation is you have to worry about time scale, because when you do plot the time scales for the sun, so this is here roughly in seconds, you have different time scales, thermal, viscous time scale, and if you want to do realistically, you want to resolve them in your simulation. So you want that your simulation is thermally and viscously relaxed. So, and when you do simulations, you have to worry about your time step and your simulation time. And it should be now that most relevant timescales are in between. But this is actually not that easy, even though if you go to quite low Reynolds numbers and stuff, to end up really in there, it's not always possible. If you use certain quantity, if you use similar setup to the sun. So what we basically do is we increase the energy input. When we run a simulation, we have run a convection simulation basically. So you put in heat input from the bottom. So we have a constant heat flux, which is should be basically for the sun, the solar luminosity. But if you would do this, your time scale will not fall into your simulation. So what we normally do, we increase the luminosity quite a lot to have the time scales closer together. But if you do this, you want, of course, that your certain non-dimensional numbers stay the same. So therefore, you have to increase rotation and other parameters. And to do this in a smart way, it's not that easy. And in the solar community, not so many people like actually these non-dimensional numbers. So for them, they often try to just use the solar luminosity and still use lower Reynolds number or whatever. And they often, the simulation might be not thermally relaxed because they use the same luminosity. So what you basically do is here, when you do simulations, you move this bit in this way, how you want to resolve your time scales. But this is just a so before we come now to the actually some results or some Dynamo thing, I just want to talk about the pencil code. So we have this very nice logo because of the pencils. This has to do with how actually the code is written. So how the loops, how it's solved. To show you a bit more, I just show you our webpage. So if you just type in basically in Google pencil code, you will have certain. Most of them are related to our code. So so we have a homepage which looks like this. So the pencil code is basically a high order code for compressible MHD. And it's a finite difference code. So what does it mean? So we basically, our derivatives are based on finite difference. So you have, currently most used is a sixth order in space. So to calculate the derivatives at a certain point, you take 3 points on each side and calculate from them the derivative. For the time, we use normally a Runge-Kutta scheme, the third order. So, and they together seem to be, it's proven to be very nice, stable, and accurate. And yeah, as I said, we can use compressible MHD. So we don't have to do simplification as unelastic or Boussinesque. So we can do the full equations. Yes. So so if you're interested in the code, it's an open code. Everybody can use it. I will show you also where you can download it. Everybody is invited also to help improving the code. And so if you're interested, just look at the website Pencil Codes. There's some news items, documentation. So we have a big manual, which is actually automatically updated if someone do some more changes to the code. We have different highlights, samples. You can actually easily go to the samples, and so if you download the code, then you can easily try one of these samples or testing things very easily on your own computer. So 1D simulations or something like this. We have automatic auto tests. So because the code, everybody who's signed up are allowed to change things in the code. We have to take care that the code is still running. So we have a couple of auto tests which run Some of them run every hour, some of them run every day to check certain samples. Are they compiling? Are they still giving the same results as 10 years ago? And for this, we always can check if something has been screwed up code. This is how we download it. We have always meetings. Okay, this is not so important. So important thing is, so we are now on GitHub also. I don't know if you talked about GitHub, yeah. So this is the code. We have around 54 contributors at the moment, but there's around 100 people basically using the code worldwide. The code is organized like this, that you have different modules. You have different models which basically give you different physics. I don't want to go into details, but it's easily to choose if you want to do an MHD run, an HD run, if you want to include particles in the code, if you want to do different geometries, everything. So it's actually quite easy to use. And if you have any question to this further, I'm happy to tell you more about it, the code in detail. So the code is, to show some examples, is also used for planet formation. So one of our colleagues, Anders Johansson, use it for actually to explain the clustering of particles to form actually planets. So, and this is, he was one of the ones who actually got the first Nature paper with our code, where we had very happy about it. So what he is doing, he uses a box simulation. He puts a box in an accretion disk, and because of the boundary condition, it's called the shearing box approach. He can basically simulate the whole, nearly the whole accretion disk just with this box. It's a bit more complicated, but so he finds the accumulation of clusters and can form basically planets with this. Another approach is, this is from one of my very early simulation, is that you can also with box simulation you can form large-scale dynamos without convection. So what you can do is you add a certain forcing at a certain wave scale to the flow, so to create turbulence, and then you can generate a large-scale magnetic field. Which is seen here, this, and then the feed lines. Some feed lines. This is now a visualization with wafer. With the pencil code is also, we have included analysis tools with IDL, Python, and also Julia. A new visualization program, which are also, most of the routines are already there. So you can just go there and basically use the routines to plot them. And all in the samples, what I showed before, most of them have actually already IDL routines checked in. So if you check out the code, you have them there. You can run the samples, can plot, run these IDL routines, and you can plot already lots of them, the outcome. Another approach is also one of my simulation is you can use it to do a spontaneous formation of a flux concentration. So this is just turbulence with form magnetic fields spontaneously, which might be important for actually the formation of sunspots. You can go to spherical shells. You can produce also something like this, ejection of magnetic helicity. So there are lots of different things, and you can of course run also convection simulation. These are now flux concentration generated by convection. So there's a whole bunch of things. People also use it for actually turbulent ring formation, for turbulent combustion, lots of different approaches. And when we wrote the code, is actually we try to wrote it like this. This is easy to understand and easy to use. And I think compared to lots of other codes, it's quite easy to use. And everybody who has more question about it, I'm happy to answer and show them more details. But already just going to the homepage, I think lots of things might be well explained. Okay. So now coming back to the global convective dynamo simulations. So these are basically the equation what we solve. So we use the induction equation with the vector potential, which helps us because then always divergence B is 0. So we don't need any divergence cleaning. It might be, the problem is you have to choose a gauge, which might be sometimes problematic. But on the other hand, yeah, and also if you formulate boundary, you have to formulate boundary condition always in the terms of the vector potential, which might be in spherical coordinates for second derivatives, sometimes a bit. But otherwise, it turned out to be very good to use this. And because we do compressible MHD, we solve the full continue equation like this. And this is our typical momentum equation with the gravity, Curie's force, Lorentz force, pressure force, and viscous diffusion. Then we solve for the energy, we solve this in terms of the entropy. So we have the normal heat conduction. Sometimes we add kind of a turbulent heat conduction terms like this to keep the code stable and to basically account for turbulent heat transport, which is not resolved in our simulation. And we have the viscous heating, Joule heating, and often we don't set the temperature fixed at the surface. Often we use a cooling function in the energy equation to keep the temperature fixed. Another, sometimes we also do that we, at the boundary, use a black body boundary condition to account for that all the heat is radiated away. So the temperature can actually change at the surface. So it's not fixed. Yeah, and we use the pencil code. So this is the link for the tutorial. And yeah, I forgot to mention that the code scales very well. So we have tested up to 60,000 cores or even higher on the supercomputers with different setups. So so when we do global convective dynamo simulations, because yeah, we are using finite difference scheme, it's very hard to do the poles. So we actually skip the poles here. And normally what we also do to save some resolution, we go just to a quarter of the speed and then apply periodic boundary condition. So it means we kind of enforce an axisymmetric solution. And yeah, this is a real plot. So how it basically looks like. So we're basically solving this, and what comes out here goes in back. So this is one of the setups. So here's the lower bottom of the equation, the higher the surface, and this is basically what we use for the pressure and the temperature. And you see, we don't really go to this high density contrast as we should do if we do it realistically. But this is one, yeah, of the with all the simulations, just to give you a thing. Just to get your impression. So, and what you basically do, we start normally with an isentropic atmosphere, so that the entropy gradient is 0, and because of the cooling at the surface and the heat at the bottom, slowly the temperature, the entropy change like this, that you have a negative entropy gradient, will keep standard convection going, and then you have a convection going up. So a typical diagram for the fluxes, very important. So this is here again the radius, and here is the fluxes in terms of the luminosity or in terms of the energy you put in. And you have here is the convective flux. So you're mostly in the upper part dominated by convection. You have the radiative flux, so the radiated diffusion, so the K grad T term. This goes very sharply down like this, and often we use enhanced turbulent diffusion on the bottom to transport out the heat, to take care that actually your scales are much smaller in the substance. So this will have a Nusselt number, Nusselt number of around 1 here, and here is a bit lower.
If I'm not mistaken, no, it's much higher than 1. I mean, this number cannot be lower than 1 anyway. Right? So it's 1 if it's purely radiative. So it's
it's not to the total. Okay.
At 0.7, when you have 1, the total flux is equal to the radiative.
Here it's much.
Here it's huge. It's
Yeah.
probably, I don't know, 100 or maybe less.
Yes. Something. So, and of course, you can also do some parameter studies. So this is some simulation where you increase here in the stratification, and you go down. You increase the stratification, you get much smaller features. And if you increase, of course, the rotation, then you get more of these banana cells features. But this is nothing really new. So important is, of course, how you want to describe the cycles and this, and taking use of the differential rotation. So this is one of our simulations. So this shows the magnetic field and the surface, and you see actually in this simulation we got lucky and can reproduce actually some equator one migration to the activity belt. So you form here a blue layer, which then slowly move to the equator. But this is actually run in this quarter, and then to visualize it, you have multiplied it by 4. If you plot it then like an average in the phi direction, you can plot it here over time. And so we were able to reproduce some part of this equator-ward migration pattern, which looks quite similar with observed. However, the differential rotation looks a bit different than the sun. But let me just tell you a bit more general about dynamos in the stellar case. So what you normally start from is the reduction equation. And so it has been appropriate for the sun, who is axisymmetric, to apply what's called mean field theory. So what you do is basically you divide your fields in an axisymmetric part. So you average them around, so in the phi direction. So then you get the overbar here, and then you have fluctuation from this. And because you're interested in the evolution of the large-scale magnetic field, so this overbar here, or the mean magnetic field, you can write it in this term. So if you just rewrite this equation using this, you get out this. And it means you have the normal diffusion here. You have the U cross B term in this sense with a large-scale magnetic, large-scale flow, large-scale magnetic field. But you have also a term which is called the electromotive force, or the turbulent electromotive force, which is the correlation of the fluctuations. And this has important effect. And so when you want to apply this equation to the sun, you can rewrite this equation in these terms, and then it's actually quite clear. You have one term which is related to shear, which is this term, which can amplify your magnetic field. So that's the differential rotation. And one term is related to the advection of the magnetic field. So, and in the sun and in other stars, there's what is called a meridional circulation. So you have flows near the surface, which goes from the equator to the poles, and somewhere, we don't know at the moment, they're going basically down, turning over in the convection zone. And these flow might be important to actually transport magnetic field and important for the dynamic process. So this is this term. But the other term is actually also very important. So the electromotive force. And if you then write it in terms of the mean magnetic field, you have lots of different terms here, quite complicated. So one goes with the linear with B, one goes with the derivatives here, And just to shed a bit light on it, I don't want to go into details. So this is the alpha effect, what Uli talks about roughly on Monday. You have other effect. The beta is a turbulent diffusion. And the other effects I will skip because they're complicated. So what people normally do, they do simplification. And now maybe this equation is a bit more familiar to you. So if you then assume a constant alpha and a constant beta, which is then a turbulent diffusion, you can plug it in this equation. So you can then use the approach, because your axis is symmetric, you can divide your field into a poloidal part and a toroidal part, like you see. And then you can split off these equations, and then you have two simple equations. The simple equations are for the poloidal field, you have the alpha term, which comes from toroidal field and some diffusion. For the toroidal field, we have an alpha effect, which gives you the poloidal field, but you also have a field related to the differential rotation. So this is the sheet. And what you can then do is, then if you can classify these dynamos. So if you say that this alpha effect is not really important, then you have just the alpha and the omega, and you call it the alpha omega dynamo. It's currently believed to work in the sun and most of the stars. In planets or in fast rotating stars, the differential rotation is often not so large, so you skip this term and you call it the alpha squared dynamo because you have here alpha and there alpha. So what people have done over, I would say, not 50 years, but maybe 30, 40 years, they have tried to model the solar dynamo or stellar dynamos by finding profiles, values for these alphas. For the sun, they're getting, of course, a differential rotation from observation, but they try to model, use here profiles or certain relation to turbulent concepts to actually model the solar magnetic field. So these are two examples, and you can produce quite well some features equate what vibration of the field. So this is the toroidal field here over time for different simulations. The problem is that all these solutions are not unique. So you can find a very different parameter sets choosing of the alpha and how the profile looks like, how your diffusion looks like, which all give you similar results. Which all give you, if you tweak your parameters right, you will always get these results. So this is the tricky part, that this, because the system is so complex, the solution is not unique. You can go from different direction to it.
Just a question.
Yeah?
That's the case when you think that they are scalars formed by the dynamo.
Yes.
But if they are vectors, then two things.
I come to this. So what we did, for example, so I showed you the one simulation of the convective dynamo simulations, where we have this nice equator-ward migration, and we can apply a technique. I don't want to go in details from this, from Martin Schöner, where you can actually calculate the alphas and plot them here. So the full tensor of the alphas. And you will see, just by looking at it, it's not that simple. So all these, so you have the alpha r, alpha theta theta, alpha phi phi, which all have different different mechanism of producing magnetic fields. And yeah, this is just some manual cards. I don't want to go in details to this. I just want to show you that the picture is not really that easy. So if you now use these calculations, these tensors, and try to calculate, oh, what are my mean generators of magnetic field? So this is for the simulation. So this is the omega effect. So producing different values of field. You have the alpha effect for the toroidal field, and you have the diffusion. You have the different mean components, and this is for the alpha effect for the poloidal field. So you see, you have even an omega term which plays a strong role, but at the same time you have an alpha effect which actually sometimes enhances, sometimes decreases this effect. So it's a very, maybe I sounds a bit too bad, but it's a very complicated picture. And I have the feeling just doing like some profiles for alpha will not give you the result. So one way is really to analyze simulations and try to find out what happens in these simulations, to find out what are the main contribution for the dynamo. And if I imagine that the simulation I showed you, they are of course not in the parameter regime as the sun, but they are turbulent, and but the magnetic Reynolds number and the other Reynolds number are in the sun much larger. So I would expect that the picture becomes even more complicated if you go to this parameter regimes. So it means like this behavior, which is already simplified here, might be even more complicated. But I think there's hope. So the hope is actually coming from observations of stars. So when you look at observe stars, and you can measure the X-ray luminosity of stars, and the X-ray luminosity seems to be, or it's thought to be related to the magnetic activity. So I plotted here, so every point is a different star. I plotted here the measure of rotation, motion of activity for lots of different stars. And you see you have a general behavior that you have an increase of activity in this rotation to a certain level, and then a kind of saturation. So it means that all these stars should have some similar mechanism that explain you this relation. So there is a hope that there's some simple picture, maybe not simple picture, but some kind of simple dependence on parameters because of this. Another plot is how does the cycle length look like. So it's also stars again. It's a bit complicated plot. So here's again the activity. So when it goes in this direction, you have larger activities. And here's the cycle when you have cyclic magnetic fields plotted over the rotation rate. And what you see here for different stars that you seem to have two distinct branches which follow certain lines. So it also means that there should be some uniqueness, or uniqueness is the wrong word, but some kind of parameter regime or some kind of relation to parameters which can explain this. So something which is actually at the end not so complicated as you think. But at the moment, it's actually not really clear why you have these two distinct branches. Okay, with this, I come to the conclusion. So the solar dynamo produces a cyclic magnetic field. For other stars, we see it that we have some of them have cycles, some don't. We have a large density and pressure contrast in the convection zone. That this pressure scale height varies from a lot in the convection zone. I talked a bit about the Pensacote, and mean field approach for the star seems to be a good approach to try to get an understanding of some dynamo mechanism. Yes, solar and stellar might be complicated, but the observation gives us hope that there might be a more simple picture. Okay, first, and now, I don't know how long. Oh, less than an hour. Okay, thank you.
Yeah, thanks a lot for this interesting talk. I guess you have a question. Yeah, Fabian.
You show that there is a dependence on the alpha omega and the alpha square depending on the rotation. If you can neglect the rotation or not.
Yes, the differential rotation.
Yes. That's for the convection zone, yes. But if you go farther from that direction, if you go towards the corona,
yeah,
you may still have the alpha effect to some
I mean, for the alpha effect, you need in the simple, in a simplistic approach to characterize the alpha effect. The alpha effect is related to the kinetic helicity.
Of course, but
So you need rotational influence.
Of course, but if you consider the magnetic helicity with it.
Yeah, but so okay, yeah. So you have in the corona localized strong magnetic helicities, maybe. But what is actually important for the alpha effect to have importance for the mean magnetic field is a mean quantity. So you have to make an average of the magnetic helicity over basically over the phi direction. And then you will probably see that, and maybe also over time, and then you will probably see that you have not strong effects there because the average out.
The alpha that you presented is not the average of the kinetic plus the magnetic helicity.
Which alpha?
The alpha and the mean field.
Yeah, okay, this is a bit more complex. But this is just to have the alpha with the kinetic and magnetic helicity. This is just a very simple approach. This is basically you assume isotropic turbulence, but you don't have if you just apply a magnetic field. So it's a very it's just to give you a what do you say, a very simple understanding what the alpha could be, but it's not a full picture, of course. And if I show you the tensor of the alpha, you will actually see that they don't really agree much with the kinetic helicity. So there's a
Let's sort this out later. The two
Yeah.
are in the same group, basically. Are there more questions? Yes.
You often consider the magnetic field as axisymmetric, but
Yes.
is the solar magnetic field really axisymmetric? Do you know that?
I mean, what you, yeah, I mean, this is, yeah, the mean magnetic field seems to be quite well accessible.
But because you average over phi,
Yeah, yeah, yeah.
definition is axisymmetric. So
Yes,
that's
yes,
really
yes.
An important
Yes.
No, I mean,
What is the ratio of RMS axisymmetric to non-axisymmetric?
yes.
Yeah.
I mean, to have this mean field approach, you use you make an average phi. So,
I mean, then it doesn't matter with which one is stronger.
yes.
Which one is-
So for this mean field approach,
Understand
so
how
this
the
is not,
two interact.
so this actually works, yeah, so by modeling this, so you don't lose anything by doing this mean field approach. This is a full picture, because the thing what you just assume is they're called Reynolds roots, so how you can multiply certain coefficients and stuff. And if you use the average and phi as your mean, the
You can
Reynolds
always
result-
separate two, but you didn't answer the question. So how strong is the axisymmetric field compared to other field components? Is it like in Earth or most planets, it's dominant, right? In the sun,
Yeah, in our I think
it's
also
very weak,
dominant,
right?
Yes.
Well, it depends on which scale you look at.
Yes.
If you look at the sunspots, the field is much stronger than orders of magnitude than in the axisymmetric field, right? So
Yes. But yeah, we don't really. You can still have fluctuation, so you can have still non-axis symmetric.
But I guess
yes.
the idea behind it is also that you want to explain the cycle.
Yes.
The cycle is something you observe in the axisymmetric field. So it's
Yes,
basically
exactly.
background dipole field, which makes it a cycle, right?
But we don't.
Yes,
I mean, yeah, of course. I mean, in our simulations, because we just take a square of the sphere, we of course suppress non-axis symmetric fields. Actually, this simulation, what I showed, was have this nice equator-ward migration. If you actually multiply it, I mean, do the same simulation with the whole sphere, you get a different picture, and you get actually non-axis symmetric fields because we're actually rotating faster than the sun. So it's a valid concern that, of course, we with the simulation setup we basically just enforce axis symmetric field, but with the mean field approach, not really. So this is actually.
Would it make sense to use the pencil code for what we are doing, planetary dynamos? Is there any advantage of doing that? I mean, you have to leave away the polar cap. That's what you've shown, right? And so, okay, if you're not interested in the poles, maybe that's still okay. I don't know. So would it make sense? So would we be able to go to lower equal numbers or run our problems faster than with magic?
I mean, if you want to do the full planet, or the full,
Yeah.
I would say that maybe magic.
I mean, you're trying to take
Because
part in
you
the.
usually don't have this strong density contrast,
Yes.
and so you lose a lot.
No, I mean, well,
Things
for,
you
for,
would-
for Jupiter, for example, we
Yeah.
use even stronger density contrast than Jörn is typically
Yeah.
using in his simulations, right? So it's there.
Yeah, I mean, you have
So-
to take. Yeah, I mean, we also. Yeah, I mean, I think for exactly when the poles are important, then this might be better to use as spherical harmonics and stuff. And,
I guess the question I'm having is if you use unelastic, I guess you have an unelastic version of the code, right?
yeah, we have.
Yes. So if you would use this or
Yeah.
ours,
Yeah.
and you say, okay, I forget about the pole problem, would you be able to run a simulation, a given simulation, at a given problem that's faster with pencil than with magic? So is there any advantage of using pencil for these problems?
I don't know. Probably not.
You have to resolve sound waves because it's compressed. It gives you some
Yeah, well, that's why
for the time step.
Yeah, that's what I meant. They have an unelastic version. So let's suppose
Yes, but just,
we use these.
okay.
And we also have, magic is also unelastic, so you can use an unelastic version of magic. It's in the code.
I mean,
right?
if you go to very high density stratification also, then you have to program with the time step. So this what I showed.
Yeah,
the
yeah,
simulation
but that's
here.
the same problem we have as well. So,
Okay.
so I guess maybe you have a comment on that as well. I don't know.
No, really on that. Well, the comment on what you said about the field on sunspots being much stronger
Yes.
than the axisymmetric component. Actually, I believe that subsurface for the toroidal field.
Yeah, you're right.
Sort of
Yes, that's right. So,
And my question is, in this kind of simulations or in this kind of simulations where you take the axis of the limited approach,
Mhm.
and you be suppressing the way of generating colloidal field, the backplane way of generating colloidal field, where really thick tubes come to the surface and then you field angle to the sunspot grooves. Are you seeing that in your simulations?
No, I mean the. You mean in the global simulation, not the mean field.
Yeah.
So I mean we don't really get already sunspots because the resolution is not high enough. So we don't see any really thin tubes or something. So this is not clear at the moment. There are other people doing similar simulation. They see quite strong what I would call flux ropes. So quite strong ropes which actually, because of the convection, can rise to the surface. And they reproduce similar tilts, actually. But, I mean, basically, so the Bach-Gleiten effect have to be also be able to express in this mean field picture, because it's a mean field theory, which is just more phenomenologically. So, I think so. I don't know if I don't know if I mean, I think so. For the Bach-Gleiten effect, it's very important to have distinct flux concentration and distinct surface effects play a role. So, and this is at least at the moment not covered in any of these global simulations.
Yeah. So my question was related to. It seems to me from your thought that the so to say normal alpha effect would compete with the Bach-Gleiten picture, or maybe one of them being dominant on the sun.
I mean the
comparison between those two.
yeah. I mean this is a bit like this. So the question is, I mean, you would have, because you have some kind of we have magnetic helicity. You normally think you might have a typical turbulent alpha effect in the sun. And the thing is that a Bach-Gleiten effect is also an alpha effect. So, but acting on a different scale and have maybe a bit different properties. But so they don't have to exclude each other really. So I don't know. I think this is a bit because this. I mean, what I showed you was the equation, the electromotive force, and then maybe you do expansion in B. So basically, the backproduct had to be expressed in this sense. Otherwise, because they can't come from nothing, they have to come from the equations. So I think there's not a real big conflicts in this. It's just the way how you. Maybe the backproduct is more like a what do you say, a toy picture of.
So that is again more an expert discussion that we can continue every day from here. So,
yeah, but your question. So, to be honest, I would say so. The pencil code is very good if you want to also if you want to do simulation for details. So, if you want to put a box in your planet and want to see how detailed, if you do high resolution convection in a box to make a parameter study how convection looks, then the pencil code is, I think, very good. Yeah, if you want to do, if you want things like compressible becomes important, this might be also important. But if I think for the, I mean, the pencil code is code which is very good in lots of things, but also not good in some things. So why not then
like
using
like ours,
like yours? Yeah. So and your code is more specialized actually for the planets. And run probably also faster for this. I don't know. So then why don't use this then codes there? I mean, it's not, you can't expect to have one code who do everything.
No, of course. That would be very boring.
Yeah.
One last question: why is it called the pencil code?
This is because like this you solve how the loops and when you have your grid, how it's organized, how you do your derivatives. So it does actually work on pencils. So it says pencils in the x direction, and along each pencil, so they solve first the derivatives in the y and z direction, and then afterwards they sum them up in the x direction. So it's basically how they organize the code, and we have in the code actually variables who are called pencils because they are long. They just have the dimension of x. And so you basically loop them over the y and z. That's what it's called.
It's connected to the memory management that you have all these 1D pencils always in your cat, and you can be very fast operating with it.
Exactly. So in a way, what Nick Featherstone is doing is similar. Yeah. Okay. Thanks a lot. Yeah. Thank you. Okay.
Yeah.
So it's time to wrap up. Okay, so after 2.5 days, everybody is a bit exhausted. Nevertheless, we hope that you've learned something here. I definitely have learned a lot. I think Thomas is still learning. He's looking for some problems. Some problems. So we will continue. And I hope you will continue as well. And if things go optimal, you will start using the code. That would be our hope. And of course, we are willing to help. So we have the online manual, and we keep on updating the online manual, actually, whenever something occurs. And we always try to make it better, to include more stuff, to make it easier. But of course, you will run into problems, as we did during this workshop, actually. There are always some problems, some unexpected stuff. And please feel free to contact us, right? So that's really part of the whole idea, that we try to answer your questions as quickly as possible, right? And our experience is also very good for everybody if more people use the code, because they will find mistakes. There are always mistakes in the codes, always. And you cannot find them, because there are, a lot of different parameter combinations and computers and everything that you may use, right? So we cannot cover that. But the more people use the code, the more likely it is that they find the mistakes in the code, right? So So the more people join the group, the better for everyone. Okay, and as a wrap up, basically, I tried to give you some ideas what the code can do and what it cannot do. So, for example, you can explore parameter spaces. We're changing all the parameters in the code, and we try to start doing that here. And this is, of course, very important because, as you learned, you cannot simulate the parameters of the planets directly. That's not possible. So you have to learn how your quantities that you're solving for depend on the parameters, and then hopefully develop some idea how you can extrapolate the results to the planets. And then if you find that the extrapolation predicts a magnetic field which is much too strong, then you have to rethink. You have to change something in your setup, right? However, if you find you predict the right magnetic field, that's a good indicator that you may work in the right regime already, though the parameters are not the correct ones. So, well, we already touched that briefly. We can use an anelastic approximation. Thomas built this in, so you can use this to simulate gas giants, but also actually to simulate stars. And you can use, well, you can use an outer stratified layer. So let's suppose you have a layer on top of the convecting layer, which is straightly stratified, like the radiative zone in the sun. There are easy ways to model that. They're not perfect, but we did this already to model fields of magnetic fields of Saturn, of Mercury, and maybe that's also an important feature for Earth. Thomas is working on some ideas to improve that in the world. So you can look at inhomogeneous chromatic boundary heat flux or temperature. So as I told you already, the Earth mantle is not homogeneous. So don't expect the heat flux to the outer boundary of the dynamo to be homogeneous. And this can have very interesting effects. You can study statistical properties of your time variations, and you can look at reversals, for example, at sacral variation. For Earth, all these features are largely not understood. So you can also use this for testing actually ideas about Earth's magnetic field, in particular about flow inversions. You know, I just talked to Siki about it. So for Earth, what you do is you measure the changes in the magnetic field, and then you assume that they are just caused by advection of the magnetic field by the convective flow. On certain timescales, that's maybe is a good idea to actually extrapolate or invert for the flow at top of the core. You can test these ideas with dynamo simulations because you have all the information there. You have the flow field and you have the magnetic field, right? So you can simulate stellar dynamos and also star sports. I come to that. Well, you can also look at more fundamental problems like how does convection work at all? How does it change with the Rayleigh number? What is turbulence and stuff like that? Well, all of course in the spherical shell. And you can also help to understand laboratory experiments. What you cannot do is, well, obviously non-spherical geometries. Magic is not capable of doing that. Even a spheroid or something like that, we cannot do it. You cannot, in a moment at least, model strongly stably stratified layers. That's not part of the code. Weakly stratified, yes, that's possible. We did this for Mercury, for example, for Ganymede, maybe, right? But strongly, that's not possible. At the moment, we cannot have two lasted layers. Sometimes you want to have like one layer, which is the convective zone, another one on top, which may also convect but with different properties, maybe totally different viscosity or electrical conductivity or something like that. So you may want to have two layers actually, and then they couple somehow, right? This in the moment is also not possible, but we would like to have it. We didn't find the time to do it in the moment. Maybe if you want to do it, you're welcome. Double diffusive problems. That means where you treat basically temperature and composition independently, and both somehow are effective and diffuse around. This is also not possible. What we typically do in the moment, as you know, Earth's dynamo is driven by light elements coming out of the growing in the core and also by temperature differences. What we do in the moment is we throw them both together into one variable, assuming that they have the same diffusivities. And then they basically have the same effect on buoyancy that drives convection. We have other versions of Magic which have that already built in there, but it's not in the version you will be using. So it's not in the fast new version. But again, there are plans to implement that. So let's see. So a few examples of of stuff that has been done with magic. Just very briefly, some of you may know the papers. So an old paper by Moritz Heimpel, where he just looked at convection in a thin, thin shell. Actually, this was still Boussinesque, and it was stress-free outer boundaries. And he wanted to understand how the zonal jets observed on Jupiter form. And it turns out that we get a very nice model for these jets, and we can understand how these jets are driven. The keyword is Reynolds stresses, but I have no time to explain this. So that seems to work very nicely, though the disadvantage in this simulation was we still used the Boussinesque approximation, though, of course, in gas giants, the density, background density profile changes significantly. Later on, we updated this using an analytic version that Thomas programmed, and we found the result is basically the same. So then, more or less, read the papers. Okay, then the newer stuff basically that Moritz did with Jupiter, this paper will come out soon in Nature Geoscience. He actually added something like a stably stratified, weakly stably stratified layer, I should say, to the very outer boundary. So just the outer few percent of this shell are now weakly stably stratified. And what we find then is that you have nice eddies form. So these are anticyclonic eddies, these blue ones, and they're fairly large compared to the small scale convection that you may see here in the background. This is observed on Jupiter. So you observe exactly the same type of eddies. So anticyclonic eddies with a cyclonic penumbra on Jupiter with very similar temperature structures. So we think we have a good explanation for that now. Well, Christa Söderland has used the code to model convection in Europa's subsurface, underneath the ice, the ocean, sort of be present in Europa. And what she finds is if you use parameters that may be true for this ocean, you find what is shown here. It's the heat flux that there is more heat. Red means more heat coming out in the equatorial region than at higher and lower latitudes. And this may be an explanation for the different ice structure you find on Jupiter. If you look here around the equator, you see more cracks. So maybe the ice is thinner or more brittle in this region than at higher latitudes. So that was another Nature Geoscience paper by Christa Söderland. And, well, we briefly mentioned that already. Julien Aubert published a Nature paper in 2008 where he varied the coronal boundary heat flux, and he could explain that if you average on time your flow, you end up with something like an eddy structure like this. And this would mean that the inner core is cooled on one side, where this eddy touches the inner core more efficiently than on other places. So at this place, the inner core may grow differently or faster than on other places. And that may explain what seismologists observe that the inner core indeed has a structure where the east hemisphere is different from the west hemisphere. Okay, then also we use differential responses to the coronal boundary to explain the feature observed in the Martian crustal monetization. So if you look on Mars today, there is no active dynamo, but you can look at the crustal monetization and you find that the monetization is much stronger in the southern hemisphere than in the northern hemisphere. I think they tell you something about that. And we don't really know why. There are different models. And one model we followed up is, well, maybe the dynamo worked like this, that you created much stronger magnetic field in the north, in the south, and in the north. And to get this, what you have to do is you have to use, well, it's a boundary condition, outer boundary condition, where you allow more heat to escape the core in the southern than in the northern hemisphere. Now, what's shown here is in red and blue, we show actually radial velocities. You can think of this as upwelling plumes and then downgoing. You can see that certainly convection is much more active in the southern hemisphere, and that brings actually the magnetic field shown here as field lines is much stronger in the southern hemisphere and brings it to the surface, so it becomes observable. So that was a nice model, which explains some features. At the end, we concluded it doesn't really work, but that's a different story. It doesn't work for Mars. So Another thing is that for some years we have been trying to help Dan Lathrop to explain his experiments. So you may know that Dan Lathrop, University of Maryland, has a big experiment, and we talked to Santiago about it. He worked on that experiment doing his PhD. It's basically a big sphere, 3 meters in diameter, filled with liquid sodium. In the interior, there's a 1 meter sphere, and they are rotated differentially. And by this differential rotation, you drive flow instabilities. And the question is, how do these flow instabilities look like, and could they create a magnetic field? The hope is they do. I still don't know. But the group with Santiago, they observed interesting instabilities, which are called inertial waves. We briefly touched on inertial waves. They could identify them based on the frequency, the typical key frequency of these waves. And we actually did simulations of the same setup, and we find exactly the same waves, these inertial waves, in our simulation. And we have the advantage that we know the whole flow structure, while in the experiment, we have no chance to ever measure them. So that helps a lot to understand the experiments. And this is actually topic of Ankit's thesis. You can also talk to Ankit about that. Then the similar setup, we got the idea that this may be an explanation for Saturn's magnetic field. So Saturn's magnetic field is a bit strange because it's very axisymmetric, and it's very highly concentrated at the polar caps. So there's not much magnetic field at low latitudes and around the equator, but it's very strong at the polar caps. So if you use this kind of flow instabilities here, or actually they look a little bit different. So the same setup, you just rotate the inner boundary faster than the outer boundary. That drives your flow, not convection anymore. Then you get actually flow instabilities that look like this. So it looks a little bit like convection rolls, but also it's a little bit different. So blue is a roll that rotates in this direction, and red, no, it's the other way around. In this direction, and red in this direction. It's somehow reminiscent of convection rolls, but it also has some different properties. And if you then look at the magnetic field that this would create, obviously they're very close to the inner core. This is the inner core here. And there's a lot of shear here. Actually, this, because you have differential rotation, you oppose that, you have a lot of shear, you create a lot of toroidal field here. And then these features produce a little bit of colloidal field that you could observe outside. And since these are they're small scale, they're very much attached to the inner core constant cylinder, the field is basically just produced here in this area and can only escape here in this area. So at the end, this is the field that you have outside. You can see it's fairly axisymmetric and it's very much concentrated at high latitude. So that seems to be a good model for Saturn's magnetic field, though we have no proof that there is a lot of different rotation in Saturn. And you will certainly also have convection in Saturn, so this may disturb that. But it's maybe the first good idea. And the recent paper by Dumas and our group about Jupiter's dynamo, so we used updated profiles from the Rostock group, and Randy, Martin, we discussed it with them, so they provide us with upper initial simulation about electrical conductivity profiles, and density profiles, and so forth, that you should use for Jupiter. We did that and ran our simulations as best as we could, and we came up with this solution, which here, so that's a cut through Jupiter, and what you find is that basically here, so the electrical conductivity in Jupiter decays rapidly in the outer part, so in this region here beyond that. So you can think of this region, because the electric conductivity is so small, and it doesn't contribute to producing any magnetic field, and also the Lorentz forces are very weak. So we find that in this outer part, you develop strong zonal winds, these zonal winds that you can observe on Jupiter, and in the inner part, you create the dipole field, where you don't have this strong zonal wind, which is very much Earth-like. And then the interesting feature here is at the transition zone, where obviously you have this shear between the strong zonal winds in the outer part and this more or less rigid inner part. And the conductivity is weak, but still large enough that you create a lot of toroidal field here. And these are the thick features. and we predict that these features may be observable on Jupiter. And next year, the Juno mission will arrive, and we hope that they confirm our idea. So, well, then you can also use it for modeling sunspots. And now Thomas, maybe you can say something about this. So this is a simulation by Rakesh Yadav in our group, and his goal was to explain sunspots. I think
the star spots.
Star spots,
yeah,
not the sunspots, they're too small scale.
So the point was trying to model fully convective stars or almost fully convective stars which are rapidly rotating, which in a way make them with a similar regime as gas giant planets. And what he found in this peculiar numerical simulation is that he has very strong fields in the polar region that are capable of severely quenching the flow in this region and forming some pretty large scale, some kind of star spot in the polar region. So it was pretty exciting because there are some observational evidence that this kind of feature could actually be observed in some rapidly rotating stars.
So, yeah, so the surprising thing was this developed spontaneously, right? So we still don't quite understand why it developed, but we can observe it in our simulations happening every now and then. And then the Lorentz forces are so strong here that they actually quench the radial flow. So that means convective transport of heat outward is suppressed, and therefore these spots appear colder in the observations. And that's seen in several star sections. Well, again, we don't know whether it's a good idea to use that model to explain that, but maybe it's best out there, actually. So here's another thing done by Thomas. It was on the JFM cover this year. It will be our Institute's Christmas card as well, because it looks like Christmas decoration or something. Where Thomas looked at non-rotating convection, and he drove the parameters very high. So very high radian number, he used different gravity profiles, different Prandtl numbers, and so forth. He scanned a lot of the parameters to better understand thermal convection in non-rotating spherical shells, and the result is a very nice paper that you can read JFM. Any more you want to say about that? Well, an interesting question was here in particular if you're interested in boundary layers, thermal boundary layers, and the transition to turbulence. And here's another one that you may want to talk about, because I don't know much about this.
Well, I think Mathieu would be the most.
Oh, Mathieu, you can talk about it. Mathieu, what is shown here? That's also done with Magic in your group.
I think this is a stable magnetic configuration obtained after we put a perturbation on the nodes and in a certain range of parameters we obtain this kind of stable magnetic configuration. And with other range of parameters we can obtain this structure magnetically due to magnetic rotational
Yeah, so that's another magnetic instability or magnetic flow instability thought to be important in protoplanetary disks, in galaxies, maybe also in stars, right? That was the idea here, to understand that a bit better. Okay, and that was the few examples I wanted to show, and now it's up to you. A lot of other problems out there, and as I said, we will help. Okay, this is the end of what we prepared for this workshop, but you may still have questions. So you can either ask them now or later. I don't know what's the time now. What parsed, that will be good time.
We'll upload the talks on the website.
Yeah, right. All the material will be there on the website.
Maybe an additional thing. I mean, when you install the code there, we disable the OpenMP on purpose because you have just some limited computational time. So if you want to make use of the code on a cluster in general, it's a good idea to just enable it because, well, possibly the code is hybrid, so you can use both the API in OpenMP, and well, it should make the code faster if you use it. If you have some trouble setting up the variable environment and things like that, just contact me or Object, and then we can help you with that. But in general, there is no reason to switch it off here. It was just because of the limitation of the cluster you use during this day.
You have some questions? You can always ask them later, send us emails, call us, whatever. Like, come around, come to our offices, knock at the door, and we will try to help you. Okay, then, I mean, as I said, we will have a guided tour now for those of you who want to join us. I already say thank you now. Thank you all for coming. I really enjoyed the workshop, and as I said, we were flattered that so many people were interested. And we hope that you will keep on being interested, and you will actually run the code, and we await your questions. So thank you, thanks again, and have a safe trip home for those who depart now. Thanks a lot.